Hello everyone. The title of this video is Solving Exponential Equations Using Logarithms. Alright, so in this video I'm going to be going over examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.6, called Exponential and Logarithmic Equations, and I'm under the heading Solving Exponential Equations Using Logarithms. Now each example I'm going to do is going to be either an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay, so there are going to be several kinds of exponential equations we'll see in this video. Some where there are two different bases to a power, to a variable power. Some where there's just one base to a variable power. And some that are like a quadratic equation. Alright, so we'll see a bunch of stuff. Alright, so first example I have, and we're asked to solve, right? So find the value of x. That would make this a true statement. We have 5 to the x plus 2 power equals 4 to the x power. Right. Now, I'll call this first way I'm doing it method 1, and then I'll go over a second way to do it that they go over in the text. So this first method is actually the way I prefer doing stuff like this. But if you want to do it the way they do it in the textbook, that's fine too. You end up with the same solutions. So the first step of this method is I'm going to use properties of exponents, laws of exponents, rules of exponents that you should know. I'm assuming you know. Use properties of exponents to get the equation to look like the following. I want some base to a power x equals some number, and I'll use n for number. So I want some positive base that's not 1 to just the x power equals, and then a number over here, some positive number over here. So let's do that. All right, so now 4 is already to the x power, but this 5 is to the x plus 2. I want things to be to the x power using this method. So I'm going to use a property of exponents. You see here in the exponent there's a sum, and you got to think, when do powers get added? It's when you're doing multiplication, right? So 5 to the x plus 2 power, that's the same as 5 to the x times 5 to the 2. Right? Those would make those, when you multiply them, would give you 5 to the x plus 2 power. All right, then equals 4 to the x, and then I get, I move things around using multiplication, division, right? I move things around until I get all the stuff with just the x power on one side and numbers on the other side, no variables. So all I need to do here is divide both sides by 5 to the x. So on the left side I still have 5 squared equals, on the right side we now have 4 to the x divided by 5 to the x. All right, and again, another property of exponents that will be useful here is when you divide expressions with the same power, keep that power and divide the new make the new base by dividing the old bases. And I'm going to switch sides here. So 4 to the x divided by 5 to the x, That's 4/5 to the x power. That's 4 to the x divided by 5 to the x. That's what I want. A number to the x power. That's exactly what I have here. Equals, and then you can leave it as 5 squared if you want, or write what 5 squared is. I'll just write what 5 squared is. 5 squared is 25. So I have exactly what I want right now, right? After using some properties of exponents and getting all the stuff with the x power on one side. I've got a number to the x power equal to a number. 4/5 to the x equals 25. And then here comes the using logarithms part. Change to logarithmic form. And you should know how to do this from earlier videos, earlier in this chapter of this text. Change to the equivalent logarithmic form. Right now it's in exponential form. And remember, if you have b to the x equals n, then x would be equal to the log base b of n. And that's it. There's your solution. So I change this to log form, x equals. Now this would be a logarithm with a base of 4/5, right? So a tiny base here of 4/5 of 25. And that's it. That's my solution. See, I've solved for x. Now, you may wish to use the change of base formula if you want. You can I'll say rewrite this if you wish. Most calculators, because you're going to be asked probably to round these solutions to 2 decimal places, 3 decimal places, whatever. Most calculators don't have a log base 4/5 button. They have a log base 10 log or a log base e, the natural log button. So I'm going to rewrite this using that change of base rule, which again I'm assuming you know. So instead of the log base 4/5 of 25, I'll make this the natural log of 25. But then don't forget to divide by the natural log of the original base, which was 4/5. And if you don't like having a fraction inside your logarithms, you can use that quotient rule. So the numerator is the natural log of 25. The denominator is, if I use the quotient rule, this is the natural log of 4 minus the natural log of 5. Right? All these are the same. The log base 4/5 of 25, the natural log of 25 divided by the natural log of 4/5, the natural log of 25 divided by the natural log of 4 minus the natural log of 5. All of these are the same number. And I'm going to punch one of these into a calculator and we'll round it to, say, 3 decimal places. Why not? So I'm going to go to that Desmos calculator, a free online graphing calculator. And I'll put in the natural log of 25 divided by the natural log of 4/5. Alright, that was one of the versions of my answer. And that is about negative 14.425 if I round to 3 decimal places. Alright, so back here. So there's my solution, rounded. This is an approximation. See the approximately equal to's. Alright, and that was method 1. I personally like it because it feels like a lot less writing to me than the other method. You'll see in a second when I go through the other method. But now if you want to double check this, you can plug it in, see if it works, or you can do that thing with the graphing where you graph both sides as a function and see where they meet. And the x coordinate, right, the x value of where they meet should be this negative 14.425. Let's see that. So I'll do that here. Right, second line, I'll graph y equals, the left side was 5 to the x plus 2 power. There's that graph. And the right side, y equals 4 to the x. The right side was 4 to the x. And they should be meeting over here. Actually click on them, see if we can, well, if I zoom in, maybe we can see where they meet. Should be around negative 14.4 something. 14 point. Well, you know what I'm going to do instead? I'll plot this point. So I'll call this function f of x instead. And then I'm going to call this a. And then down here I'll plot the point a comma f of a. And you see it's right on the graph, right? It's right on, they do meet. Now it looks like they meet at a lot of points, but that's going to be the one where they meet. All right, this is kind of a rough example because it's very, very tiny out here. It's hard to tell that that's the only place where they actually meet. Yeah, so I could actually show you this way instead. If I called that one f of x, I'll call this one g of x. And then let's see the values of their outputs at that solution. What's f of a? See, it's something super tiny. And then what's g of a? And you see it's the exact same thing. Where a was this negative 14.42513. So they get the exact same output for both these sides. So that is a solution of the equation. Alright, so this wasn't the best example to do that with, but still, you could use a graph to help verify a solution. Alright, so like I said, that was one method. Now, method 2 is just straight up using logarithms from the get-go, and then using some properties of logarithms. So it's the same example, but I'll do it another way. Method 2, we had 5 to the x plus 2 power equals 4 to the x. And the first step would be just, we're going to use that one-to-one property for logarithms. When two things are equal, their logs will be equal, right? If two positive numbers are equal, which these will both be positive numbers, then the logarithms of any base will be the same. So I'm going to take the logarithm, and I'll just use natural log. I'm just going to use natural. You could do log base 10, log base c. It really doesn't matter what base you choose. I'm going to take the natural log of both sides. So now we have, using the one-to-one property, this is equivalent to saying that the natural log of 5 to the x plus 2 power is equal to the natural log of 4 to the x power. All right, then I'm going to use that power property for logarithms to pull the power out, right? These are logs of powers. So I'll use the power rule, power property, power rule for logarithms. I'll just say for logs. So this quantity x plus 2 comes outside. So we have the quantity x plus 2 times, and then just the natural log of 5. All right, and the natural log of 5 is a number. I know people often get confused because of all these L's and N's and logs everywhere. Those aren't variables. Only x is the variable. When you see natural log of a number, like 5 like this is a constant. This is a number. This is 1 point something. Same thing on the other side. I pull x out. We have x times, and then just the natural log of 4. Right? And the natural log of 4 is a number. So I have x plus 2 times some number equals x times some number. And then so what we have here is a linear equation in x. Solve this equation. Solve the resulting equation for the variable, and there you go. Right. And again, I think this gets tricky for people, but over here, x plus 2, the quantity x plus 2 times natural log of 5, I got to distribute the natural log of 5. So we have x times the natural log of 5 plus 2 times the natural log of 5 equals, and then over here is still just x times the natural log of 4, right? All I did was use the distributive property to clear the parentheses. Alright, then I subtract the term to get all the terms with the variable on one side, terms without the variable on the other. So I'm going to subtract this term with the x in it, x times the natural log of 5. I'm going to do that from both sides. See, now on the right side, those two terms have x in it. So I can factor x out to get 1x by itself, right? And if I factor x out, what will be left over as the other factor would be the natural log of 4 minus the natural log of 5. And on the left side, I still have just 2 times the natural log of 5. And so what I have here is a number equals x times a number. So to get x alone, I just divide by the coefficient, divide by this number, and we get x equals 2 times the natural log of 5 in the numerator, divided by, and then this natural log of 4 minus the natural log of 5 in the denominator. And you see how this is exactly the same as what I got earlier? I could rewrite this if I wanted. Use the power rule for logs, put that 2 inside, make this the natural log of 5 squared or the natural log of 25 in the numerator. And I could use the quotient rule for logs. When you see two logs being subtracted, you can make that the log of a fraction, the natural log of 4/5 in the denominator. This is exactly what I got on the last page. Natural log of 25 divided by the natural log of 4/5. Approximately negative 14.425. Right? Or whatever they have you rounding it to. Yeah. So I don't know about you. I mean, this is fine too. I don't think it's all that terribly difficult. I just find people have a hard time when they see all these logs everywhere. When there's no variable inside the log, it's a number. The natural log of 5 is 1 point something. Same thing with the natural log of 4. That's 1 point something. Right? It's just a number. So don't treat L's and N's and O's and G's in the log word. Don't treat those like variables. Alright, so let me do that again. And actually, I'll go through the second one with both methods as well. So I have another example here like this, where both sides are written in different bases. You may recall from the last video on using like bases to solve equations. If they had the same base, then you would just equate the powers. That's really simple. But these have different bases, and I can't really think of how to write 3 as a power of 2 or 2 as a power of 3 without involving logarithms. Alright, so again, we have 2 to the x equals 3 to the x plus 1. I'm trying to solve this, find a value of x that makes both these true. So again, I'll call them method 1 and method 2. I'm not going to write the steps out again. But method 1, I want that b to the x equals n, and then I change to log form. So the left side already has, 2 to the x. It's the right side. 3 to the x plus 1 is the same thing as 3 to the x times 3 to the 1, or just 3 to the x times 3. And then I would divide both sides by 3 to the x, and that would give me 2/3 to the x. After applying the property of exponents, equals 3 on the right. And now I have what I want. Base to the x equals number. And I change to log form. So x would be equal to the log base 2/3 of 3. Which, again, usually we don't like having a fraction base. I mean, it's not wrong. This is totally correct. But most calculators, if you're going to be punching things in on a handheld calculator, most calculators have either log base 10 or log base e. So I'm going to use the change of base rule here and do natural log again. This is the natural log of 3 divided by the natural log of 2/3. And once again, if you don't like having this is fine too, but if you don't like having a fraction in your log, you can do that quotient rule. Right? So the natural log of 3 in the numerator, and in the denominator, the natural log of 2 minus the natural log of 3. Okay, and all these are the same. All three of these are the same. And let me punch this in, and we'll get our solution. I'll do the same thing where I round it to 3 decimal places. So we had the natural log of 3 in the numerator, and the natural log of 2/3 in the denominator. Oops. Alright, so that's negative 2.7095, so negative 2.710. Negative 2.71, if I rounded that to the nearest thousandth. So there's our solution. Alright. And let's test it out. Alright, I'll put in those two functions, the left side and right side. One I'll call f of x equals 2 to the x. And the other one I'll call g of x was 3 to the x plus 1. Oops, make sure x plus 1 is all in the power. Oh look, and they do tell us where it meets. This is a lot better. See, negative 2.71. X equals negative 2.71. You can clearly see where they're meeting now. So that is a valid solution to this equation. Alright, now that other method, again, you decide which one you like better. It doesn't matter to me, as you get the same result both ways. So the other method is, I start with this equation, I take the natural log of both sides. So the natural log of 2 to the x equals the natural log of 3 to the x plus 1 power. Then I apply that power rule, right? These are logs of powers, so I can pull the powers out. On the left side, I have x times the natural log of 2 equals, and on the right side, you have this whole power, so the quantity x plus 1 comes out times the natural log of 3. Alright, and the natural log of 2 is a number. It's like 0.69 something. And the natural log of 3 is a number. It's 1 point something. So I'll distribute this natural log of 3 to get rid of the parentheses on the right side there. So we have x times the natural log of 2 equals x times the natural log of 3 plus 1 times the natural log of 3, which would just be the natural log of 3. And then I would subtract this x times the natural log of 3 from both sides to get all the terms with x on one side, get them all on the left side here. So that gets rid of that term. And you see how both of these terms now have x in it, so I can factor x out. So I have x times, and then if I factor x out, what you'll be left with in the other factor will be natural log of 2 minus the natural log of 3. And then on the right side, I just have the natural log of 3 still. And this is x times some number equals some number. And I divide by that number, get x alone. And we get x equals the natural log of 3 in the numerator divided by this difference here, the natural log of 2 minus the natural log of 3. And oh, look at that. That's exactly the same as what I got here. Exactly the same as what I got in that first method. So, as I've been saying, it's up to you. It's up to you. Right. But I'm going to be doing this for a lot of these problems. I want base and power alone equal to some number. And then I change the logarithmic form and solve. Right, that's going to be happening in a lot of these. Okay. So now in the next equations, in the next few of them, I have just one base in power, right? This e to the 2t here. Now if there's just a single base in a power like this, you want to get it alone. You want to isolate it. Get it by itself, because like I said, I usually want a base in power equal to some number, and then I'll change the logarithmic form. So if I have 100 equals 20 times e to the 2t, just divide by 20, and we'll have e to the 2t equals 5. right? Just dividing both sides by 20. And now I have what I want. Base to a variable power equals some number. So I change this to log form, right? The equivalent logarithmic form, where remember the power is the log. The logs are exponents, exponents are logarithms. So 2t equals the log base e of 5. But the log base e, that's natural log. Right? So the natural log of 5, which is again some number. And then all I need for t now is to divide by 2. So the solution here is t equals the natural log of 5 divided by 2. Right? Or half of the natural log of 5, or if you put the half in as a power, it'd be natural log of 5 to the half, or the natural log of the square root of 5. All those things are the same thing. And there you go. There's what they would call the exact solution. If you don't punch it in the calculator and leave it the way it is, that's called the exact solution. So you saw in some other problems the exact solution. Then if you punch it in the calculator and round, that's an approximate solution. All right, so let's go here. I'll enter this into our calculator. The natural log of 5, this is 1 point something divided by 2. So the solution of this equation is approximately 0.805. Right? I'm just going to round all my answers to 3 decimal places. Again, just pay attention to whatever exercises you're working on. If they ask you to round to so many decimal places, just be sure to do that. Okay, wonderful. And again, if you were to plug this value in for t, if you plug the exact value in for t, you'd end up with 100 equals 100. If you plug in the rounded value for t, right, the approximate answer, then you'll have 100 equal to something that's really, really close to 100, right? It's approximately 100. All right, great. All right, and again, the next few problems are like this, where I have a base in power that I want to get alone first. So here I have 3 times e to the 0.5t, or half t, equals 11. So as I did with the previous example, this base and variable power, I would like to get this alone, isolated. So first I need to divide by 3. All right, so we have e to the half t equals 11/3. And then I change to the equivalent log form. I'll just write log. So the power, the half t, is equal to the log base e, or the natural log, of 11/3. And then just double, this is a half, so you can just multiply both sides by 2, or divide by 0.5, but that's the same thing as multiplying by 2. So I have t equals 2 times the natural log of 11/3. All right, if you want to write the natural log of 11/3 in a different way with the quotient rule, that's fine. If you want to put the power in, make it the log of 121/9, that's fine too. But this is our exact answer, our exact solution. And once again, I'm going to round this to the nearest thousandth. 2 times the natural log of 11/3. And it's about 2.599. 2.599 if I'm rounding to the nearest thousandth. Okay, and if you want to call this, say I call this t, and then we can check 3 times e raised to the 0.5t c equals 11, which is what the equation was. So that definitely is the valid solution. That's how you can check on your calculator, if you have a proper solution or not. Yeah, so check on that. Great, so number 5 is more of the same. Very similar. So you have 4 times e to the 2x. Then you have this plus 5 here, equals 12. So get this e to the 2x by itself. So first I would subtract 5. 4 times e to the 2x would be equal to 7. All right, 12 minus 5. Then divide by 4. So e to the 2x equals 7/4. All right, and now I have what I want. Base to a variable power equals some number. Change to log form, right? Change to the equivalent logarithmic form. So that power, that 2x, is equal to the log base e, or the natural log, of 7/4. And then I would just multiply both sides by a half, or divide by 2, same thing. So half the natural log of 7/4, or natural log of 7/4 divided by 2, whatever. There's your solution. All right, and once again, I'm going to round this to the nearest thousandth. So, and I'm going to call this A. A equals 1/2 times the natural log of 7/4. So if I'm rounding this to the nearest thousandth, that'd be 0.2798, so 0.28. Approximately 0.28 is the solution. And then let's test it out. So remember, I called this A, so I'm going to plug A in for x in the left side of the equation. Now the left side of the equation was 4 times e to the 2x. So 4 times e to the 2a power, and then plus 5, see how that's 12, which is what we wanted. That's what the equation said, 4 times e to the 2x, whatever x was, plus 5. That needs to be 12, and it was. So this is a valid solution. Alright, now number 6 is maybe a little trickier, but not really. Because I got some like terms here. These are both e to the same power. So I can put things together, like I can put these together. If I subtract e to the 2t from both sides, you have 3 on the left equals, and then 7 e to the 2t minus 1 e to the 2t would be 6 e to the 2t. Right, those are like terms. They have the same base and power, so you can put the coefficients together. And then I just isolate this, get the e to the 2t alone, just like in earlier problems. So I would divide by 6. We have e to the 2t equals 3 divided by 6 is a half. And now I have what I want, base to variable power equals some number. I change to the equivalent log form. So 2t equals the log base e of a half, or the natural log of a half. And then I would divide by 2, or times a half. So t equals half times the natural log of a half. There's our exact solution. And once again, I'm going to have it rounded in the calculator, and also I'll enter it into both sides here and see if we get the same value. Alright, so again, I'm going to call this just this number A, right, equals half of the natural log of a half. So negative 0.347. Approximately negative 0.347 is the solution. And again, I'll just use this calculator here to check my answer. The left side was 3 plus e to the 2t, but I'm going to call that 2a. So the left side's 3.5. The right side was 7 times e to the 2t, but I called it a, and again I get 3.5. I get 3.5 equals 3.5 when I plug this number in. So this number is making the equation true. It is a solution. Check on that. All right. Okay, so far, each of these equations, you could solve with some simple logarithms. You could all write these as a base to a power, a base to a variable power equals a number, and then change it to log form and solve. These next couple examples, you won't be able to do that with. So here, say e to the 2x minus e to the 1x. So these are not like terms. These do not have the same base and power. You cannot put these together. Equals 56. So I can't because I have these two different expressions, they're not like terms, same base but different powers, and this is not 0 over here, it's a constant. So I can't solve this like earlier problems. But I will tell you right now, this is like a quadratic equation, and I'll show you why in a second. Alright, you may remember back in talking about polynomial equations. Remember, anything that looks like this is like a quadratic equation. Some number a times u squared plus some number b times u to the first plus some number c equals 0. Anything that looks like this is like, a quadratic equation or quadratic in form. So watch this. When I take the 56 to the other side, we have e to the 2x minus e to the x minus 56 equals 0. And look at the power on this first term. You see how the power on the first term is double the power on the second term? And then you have a constant. Just like what happens in a quadratic. The power on the first term is double the power on the second term, and then you have a constant. Now, most of the time they'll tell you to make a substitution here. Let me show you the sub that you would make. Now remember, I can rewrite this first term using a property of exponents. E to the 2x is the same as e to the x to the second. Remember, power to a power, you would multiply those and get e to the 2x. Minus, and then this is, e to the x to the first. And then minus 56 equals 0. So you see this quadratic form here. This expression u squared, u to the first, is e to the x here. I'm going to let u replace e to the x, and then you're going to see it is indeed like a quadratic. This becomes u squared minus, and then e to the x again becomes u, and then minus 56 equals 0. And then I can solve this for u. All right, and I'll solve this for u, and then we'll go back and solve for x. Now you could use the quadratic formula, completing the square, or try factoring, and this one's actually nice and factorable. We have u minus 8 times u plus 7 equals 0. So either u equals positive 8 or u equals negative 7, and then now we've solved for u, we sub back. What was u? U was e to the x. So I have e to the x is equal to 8, or e to the x equals negative 7, and then we solve these for x, and of course check your solution. Solve for x, check. So here x would be equal to the natural log of 8, right, when I change it to log form. Here x would be equal to the natural log of negative 7, but that's not good. Remember, you can't have negative numbers inside a logarithm and have the output be real. You can only have positive numbers inside your log. So the only solution that works in this equation is the natural log of 8. All right, I'm going to show you. All right, so let's go to the calculator. I'm going to put in, again, I'll call it a. A equals the natural log of 8. Here's our solution, 2.079. Now the left side of that equation was e to the 2x. So e to the 2a, and then minus e to the x, so minus e to the a. And look at that, it's equal to 56, which was the other side. So that natural log of 8 is indeed a solution of this equation. It makes it true. But yeah, so this one's a little trickier, but hopefully you noticed how one power was double another power, and then you had a constant. All right, 56 there. So if you recognize that one power was double the other power, and then you had a constant somewhere as another term, maybe you'll recognize that as a quadratic-like equation, and you can solve it in such a way after making a substitution. All right, so my next example is exactly like this. All right, there's another equation that's exponential, but it can be treated like a quadratic. Right. And I believe this is the last example I have like this. Yeah, and then the rest of them are things we've seen before. All right, you just have to figure out what you're doing. So yeah, see here, this is the same as e to the 2x, minus e to the x minus 2 equals 0. And you see how this is like a quadratic. If I let u replace e to the x again, this would be u squared minus u minus 2 equals 0. And I solve for u. This factors to u minus 2 times u plus 1 equals 0. So u is equal to 2 or u is equal to negative 1. And then I sub back, meaning that e to the x equals 2 or e to the x equals negative 1. And then putting these in log form, we get x equals the natural log of 2 or x equals the natural log of negative 1. But that's a problem. That's no good. That's not real. So the only solution that's valid here is the natural log of 2. And again, we can check it. Alright, so back here again, I'll just call it a again. A equals the natural log of 2. So 0.69 something, 693. The left side was e to the 2x, so I'm going to call that e to the 2a, get 4. And then the right side, e to the a plus 2, and you see I get 4 again. Right? So if you plug this number in to the original equation, you're going to get 4 equals 4, a true statement. So this natural log of 2 is indeed a solution. Alright, but hopefully you don't come across too many of these, but just know that they're out there. Again, if you ever recognize, hey, one term has double power than another term, and then there's a constant, you can treat it just like a quadratic. Alright, now the rest of the problems are similar to ones we've already seen from examples 1 through 6, examples 1 through 6. And then we're doing more of the same of that. Alright, so for each one of these, for each one of the rest of the examples, I want to get I want to write a base to a variable power equals some number. Right? I want this base to some variable power. It doesn't have to be just the x, but I want a base to some power with a variable equal to some number. Right? We want this, and then we would change to logarithmic form and solve. And then of course check your solutions. So number 9, we have 2 times e to the 6x equals 13. To get a form like this, we just divide by 2. We have e to the 6x equals 13 halves, or 6.5, 6.5. And now I have what I want. Base to a power, a variable power, equals some number. We change to log form. This means that 6x equals the natural log, the log base e, of 13 halves. And then I would just divide both sides by 6 or multiply both sides by 1/6. Right, so x equals 1/6 times the natural log of 13 halves. And there's our solution. And again, if you want to check it out, now I'm going to stop rounding. We'll just see it in the calculator. But let's check it out. So again, I'll call this a, the number I plug in. And we had 1/6 times the natural log of 13 halves. So our solution should be 0.311967 blah blah blah. All right. Now I'm going to plug this number a into our equation. The left side was 2 times e to the 6x, so 2 times e to the 6a. And the right side was 13, and see how I get equal to 13 there. So that is a valid solution. Wonderful. Okay, something similar here. Number 10. Got 2 times and then 10 to the 9a power equals 29. Once again, I want to get that base and variable power by itself, so all I need to do first is divide by 2. We have 10 to the 9a power equals 29 halves, right, or 14.5 if you want to write a decimal. Now I have what I want, base to a variable power equals some number, and I change to log form. So 9a would be the log base 10. Remember, log base 10 is just written log with no base. The log base 10 of 29 halves. And then to get a alone, I would multiply by 1/9 or divide by 9. Right, so a equals 1/9 times the log of 29 halves. And there's your solution. And then let's check it. So again, going back to the calculator. And I'll call it a equals 1/9 times the log base 10, right, log with no base of 29 halves. So the solution here is 0.129 something. Right. And then let's just see, let's plug that in. Now the left side of the equation was 2 times 10 to the 9a power, and you see how I'm getting 29, which was the other side. So that works. That works. So check that. Okay. So 11 and 12 are pretty similar. Alright, 11. I want to get this e to a power by itself. It's the only base to a variable power I'm seeing. So first I subtract 5. We have 7 times e to the 3n minus 5 power equals, negative 94. Right, negative 89 minus 5. Then I would divide by 7. So e to the 3n minus 5 power equals, negative 94 sevenths. That does not reduce any further. And this is a problem. All right. Watch, right? When I change this to log form, we have 3n minus 5 equals the natural log of a negative number. Eep. This is not real. This is not good. So there's no solution to this equation. No real solution. So I'll write that, no real solutions. Or you could say the solution set is the empty set, but I'll just write there's no real solution. There are no real solutions to this equation. Now, as I mentioned before, if you go on in mathematics, logs of negative numbers you'll see have an imaginary part to them. They'll involve imaginary number, that I, and you could find a complex number solution with an imaginary part to it. But for right now, for our purposes of this text, there's just the log of a negative number, not real. Just stop. All right. Okay, and then this one, again, I want to isolate this e to a power. So first I would add 8. I have negative 5 times e to the 9x minus 8 equals, and then negative 62 plus 8 would be negative 54. Right. And then divide both sides by negative 5 to get that base and power alone. So e to the 9x minus 8 equals, now a negative divided by a negative is positive, right? Positive 54 fifths, or 10.8. This is fine, right, as long as there's a positive number over here when you have your base to the variable power. Then I change to log form, right, so 9x minus 8 is equal to the natural log of 54 fifths. Then I would add 8, giving me 9x equals the natural log of 54 fifths, plus 8, and then divide everything by 9. So x equals, 1/9 times the natural log of 54 fifths plus 8/9 after dividing everything by 9. And there you go. That's the solution. And you can punch that into a calculator, round it to so many decimal places, whatever, and then plug that value back in and see if it makes the statement true. And it should. I'm going to kind of stop that from now and leave the checking to you. But that should be good. Alright, then the next equation. Now I'm not going to do this one with both methods like I did before. But the next equation is one of those where you have just two bases that are different to some variable power equal to each other. And this is like the very first examples from the video, almost 50 minutes ago. So remember I solved this with two different methods, right? I'm just going to go through that first method where I want b to the x equals n. I want this, and then I'll change the log form, and then maybe use the change of base formula to write it in terms of log or natural log. So over here, 2 to the x plus 1, that's 2 to the x times 2 to the first. 5 to the 2x minus 1, when is there a difference? When you divide. That's the same thing as 5 to the 2x divided by 5 to the first. That would be 5 to the 2x minus 1. Alright, but then 5 to the 2x is really 25 to the x. Right, because that 5 to the 2x is really 5 squared to the x. Use that power to a power rule. So here's what I've got. 2 to the x times 2 equals 25 to the x times 5. Or divided by 5, sorry. Alright, then I'm going to multiply by 5. 2 times 5 is 10 on the left. And I'm going to divide by the 2 to the x, giving me 25 halves to the x on the right. And there we go. Here's my base to a power x equals a number. Exactly what I want. So I change this to logarithmic form. So the variable, the exponent x equals the log with a base of 25 halves of 10. Alright, and then we can use change of base formula to, since the input's 10, I'm going to change this to log base 10. So log base 10 of 10 would be 1 in the numerator. And then you have the log base 10 of 25 halves in the denominator, which I could write as a difference if I want. So I have 1 in the numerator, and then the log of 25 minus the log of 2 in the denominator. And if you want to think of 25 as 5 squared and pull the 2 out using the power rule, you can. This is 1 in the numerator divided by 2 times the log of 5 minus the log of 2 in the denominator. I mean, all of these are the same. These are all the same number. Alright, just using the properties of logarithms. And you can punch that number in, round to so many decimal places, whatever, and then use the calculator to test it out, see if it actually makes the original statement true. But I will leave that to you. Right, and if you want to use that other method as well, take the natural log of both sides or log base 10 of both sides, be my guest. Okay, number 14 is going to be very similar to a problem we saw earlier. First I'll add 5. We have 7 times e to the 8x plus 8 power equals, and if I add 5, that's negative 90. And I divide by 7, we have e to the 8x plus 8 equals negative 97ths, and that's a problem. All right, again, that's a problem because when I change it to logarithmic form, we're taking the natural log of a negative number, which is, again, not real. So there's no solution again. Right? This is another one of those that would have no solution. Right? No real number solutions or no real solutions. Okay. Great, and then I just got one more page where I'm basically doing the same stuff as the previous several examples. So hopefully you got what's going on by now. So here, 15, 4 times e to the 3x plus 3 minus 7, and then equals 53. So e to the 3x plus 3, must be equal to 15. Because if you add 7, that gives you 60 over here. And 60 divided by 4 is 15. Then I change the log form. 3x plus 3 must be equal to the natural log of 15. Then I would subtract 3 and divide everything by 3. Right? So x equals 1/3 times the natural log of 15 minus 1. Whatever that number is. Again, I leave it to you to punch that in, check it out from here on out. Alright, and then my final example is another one. This is exactly like example 13 and some of the first examples from this video. So once again, I'm going to use properties of exponents to get this, base to the x power equals n, and then change to log form. So 3 to the 2x plus 1, that's 3 to the 2x times 3 to the 1. 7 to the x minus 2 is 7 to the x divided by 7 squared. All right. Now 3 to the 2x is actually 9 to the x. So I have 9, 3 squared to the x. So that's 9 to the x times 3 equals 7 to the x, and then divided by, 7 squared is 49. Then in a very similar fashion, I'm going to multiply by 49. That would be 147, right? 3 times 49, so 147 on the left. And then divide by 9 to the x, giving me 7/9 to the x on the right. And then I can change to log form. X would be equal to the log base 7/9 of 147. And if you don't like that, change the base. Right? This is the same thing as the natural log of 147 divided by the natural log of 7/9. And if you don't like the natural log of 7/9, you can rewrite that. That's the natural log of 147 divided by, and then in the denominator we have natural log of 7 minus the natural log of 9. And again, all these are the same thing. They're all the same number. And once again, I'll leave it to you to check that whatever this number is, when you plug it into this equation, it makes it true. All right, but I'll leave it to you to check that on the Desmos calculator or whatever calculator you have. Alright, so that was a lot there. I know I kind of rushed through the last few, but I'm hoping by this point, after the first like 9-10 examples, you get what's going on. Yeah, so hopefully watching me go through these 16 examples here helps you out in some way when you're trying to use logarithms and properties of exponents, properties of logs, to solve exponential equations yourself. And thank you very much for watching.